Alright, so we're going to understand the relative measures of any angles as the length of the arc of a unit circle subtended by the angle. We will explain how the unit circle in the coordinate plane enables the extension of the trigonometric functions to all real numbers, interpreted as radian measure of angles traverse counterclockwise around the unit circle. That is what we're going to be focused on today. And I guess today I decided to go ahead and break down what the standard is, just so you could just kind of see where is this coming from. And again, just for a reminder, as I teach, I tie stuff from your Eureka lessons into this as well. Reminders, tutor is still happening Tuesdays and Thursdays from 5 to 5:30 p.m. Now, I understand the Chromebooks got missing. They took them. Okay, I get it, understand. But if you truly want to learn, truly want to master this material, because it's going to pick up. It already is, because you guys are going to be tested left and right. Speaking of which, we do have pop quizzes, and then we're going to have a quiz, a regular quiz, next week. Just to see what you guys gonna do. I know you're like, Mr. Howard, can I review with you? No, you ain't gonna have a whole day of review because, believe it or not, in the rotations, I already include stuff that you already been taught. All right, updates. So the quiz is actually gonna be November 6th and November 6th and November 7th. At your last stick, we have the Chromebooks and not paper. Most likely, I'm gonna have the Chromebooks, so at your last stick. All right. So for your project one, I know they took Chromebooks away, but time will be allowed. 2 class periods to work on the project one. That does not mean, let me emphasize, this does not mean 2 whole class periods. No. I may give you a piece of a moment and give you another piece of a moment. That's just that because by now you should have already been ahead of project two. I mean one. Have all the details. When you are absent, as long as you got documentation, you're approved to do makeup work. But because of the whole Chromebook situation, you may have to come to another class to do makeup work. Alright, so the binder check that's coming up, which is going to be November 2nd and November 3rd. I'm looking for the notes from the 26th through the 1st. 26th, I'm aware that I was absent, so the 27th. I'm looking for these notes. And that includes handouts and ACT stuff as well. So anything ACT related, I gotta see it. Alright? So just a reminder, we gotta talk about the Pythagorean. So the 3069 triangle, we have noticed the hypotenuse is twice the short leg. So if the short leg is 11, the hypotenuse of this is 11 times 2, which makes it 22. And then the long leg is going to be the short leg times square root 3. So 11 times square root 3. And that's when you have the real long leg. The 45, 45, 90, both of the legs are going to have equal amount. The hypotenuse is going to be the leg times square root of 2. Alright, this right here, this is just no way of saying by the 30, 60, 90 and the right isosceles triangle, which we know is a 45, 45, 90. Again, yeah, I am writing this with the mouse, so I'm sorry about that. So remember, for the 30, 60, 90 is twice the short leg, and then the long leg is the short leg times square root 3. Alright? So let's look at the isosceles triangle, which is your 45. So if my long leg is 11, what's going to be my short leg? What's going to be my hypotenuse? Well, we know that if one leg is 11, the other one's going to be 11. And the hypotenuse is going to be 11 times square root of 2. Alright? Alright, so let's review right quick. Let's find the size, missing side, and do the 6 trig ratios. So the hypotenuse, because I can read that the best, is going to be 5 square root 2, right? And we know the hypotenuse is the leg times square root 2. So the leg of this is just going to be 5. So if 5 is going to be the short leg, but then 5 is also going to be the long leg too. So they're both going to have equal measures. So now, let's do the 6 trig ratios. So sine is going to be 5 over 5 square root 2, which we know if it's sine, also the hypotenuse. However, something I told you that you can never, ever, ever, forever, ever, ever, ever happen. Having the square root in your denominator. So, we gotta multiply both numerators and denominator by the square root of 2. So let me change my color. Again, I am writing with the mouse, so I do sorry about that. So 5 times square root of 2, well, you can't multiply those together, so it's going to be 5 square root 2. However, 2 times 2, square root 2 times square root 2 is the square root of 4. But I'm going to have 5 right here. So it looks like to me we can make some things cancel and simplify, right? So the square root of 4, well, before we do that, those 5's can cancel out. Because 5 divided by 5 is 1, so that cancels out. So we are left with the square root 2 over the square root of 4, which we know the square root of 4 is just 2, and we know that the square root of 2 is just square root of 2. So that's my final answer for sine. Let me erase. Again, I know, Mr. Howard, we don't understand your handwriting. Oh my God. Yes. However, I'm telling you what I am writing on the screen so you can understand that. So, my final answer is going to be right here. Square root 2 over 2. That is my final answer. And that's for sine. Alright, so let's do the inverse of sine. The inverse of sine is what? CSC, cosecant. So we had, if sine was square root 2 over 2, or then cosecant, which is the inverse of sine, is square root 2. No, you gotta flip it over. My bad. So it's gonna be 2 square root 2. But there's something that I'm gonna have an issue with. Is that square root of 2 in the denominator. We can't have that to happen. So to do that, multiply by the square root of 2 on both of these. And when we do that, we get 2 times square root of 2, which is just 2 times the square root of 2. And then square root of 2 times square root of 2 is just the square root of 4. So, but we could simplify square root of 4 to be what? 2. And then we're going to have 2 times square root of 2. Something that could cancel out. 2 over 2. So, your final answer for cosecant is just going to be the square root of 2. So I'm doing my dots the best I can. Again, I'm doing this with a mouse, y'all. So I do not have a stylus. So that's my answer. Now, I did one of them. Now you are going to do this video yourself for this particular part and give me the rest of those trig ratios. I gave you two. I gave you sine, and the inverse is called cosecant. Circles in the Pythagorean. Now, we're going to flip this circle, and we're going to flip it around and turn it around into his ugly head. Alright, in order to make this happen, we have to derive the equation of a circle of a given center and radius to prove the Pythagorean theorem. So that's right, we're going to take the knowledge of the circles. So we're going to make our geometry teacher proud, and we're going to get into it. So what is a circle? Take a time to try to remember what a circle is so you can answer that question. Right. I just answered it. So let's go to it. So circle is the set of all points on a plane that has a fixed distance from the center. Now there's always a way of wording that, but that's a definition I like to use. So consider a circle with a radius r and a center hk, and we're going to create the center of the equation. So one thing I gave you guys the equation of a circle, but what you guys gonna have to know in particular, you're gonna have to know particular knowledge of how that came to be. So you have a fixed point x and y and a center hk, and the r is the distance between the two. The r is the distance between the two. All right. All right, my people. So we have to write a standard equation of a circle. So we don't know the points. However, we know that we have a center of the origin point being 0, 0, right? So we're going to take this equation and plug in 0 for x and 0 for y. And guess what happens? X squared plus y squared equals r squared. But that sounds familiar, does it? Sounds very familiar with something that you know. But we're going to get into that a little bit later. All right. So you have a 0.56 and it's on a circle with a center of 1, negative 3. I mean, negative 1, 3. And you have to write the equation of the circle. So let's do that first. So here's our equation. So the point negative 5, 6, they're going to be my h and k. I mean my x and y. And then my h and k is my center, so it's going to be negative 1, 3. So when I plug in those values, again, negative 5 was my x, and 6 was my y. H is my negative 1, and then k is my positive 3. So those are plugged in. I add them together, I get this number right here. Alright, so that's the equation. So now let's go ahead and find the radius. Again, this sounds like something that you have been dealing with all the time. And we're going to get to it momentarily. So we know negative 4 squared is what? 16. And 6 squared is 36. So when we add those together, 16 plus 36, we get 52. And when we break down 52, we get 2 with the square root of 13. So how we got 52? When we break down 52, we get 4 times 13. And we know that 4's is a perfect square of 2, so we leave that on the outside, and then 13 on the inside. And that's where we got that from. Alright, we're going to convert degrees and radians. Again, we're going to flip in the Pythagorean theorem. By now, you guys should recognize the equation of the circle. This equation of the circle and the Pythagorean theorem, they are interconnected. So here, let's convert degrees into radians. So far, we have been dealing with 3 important degrees: 30 degrees, 45 degrees, and 60 degrees. These are 3 very important degrees that we are going to be dealing with. And you're going to see them next class period a lot. So to convert from degrees to radians, you just take the number of degrees you have and times it by pi over 180. But from radians to degrees, the number of radians times 180 degrees over pi. So take a moment to write that down, keep it paused, and we're going to apply it to all what we're going to do. Alright, so let's convert some degrees to radians. So you got 10 degrees, 20 degrees, 40, 120, 240, and 330. And we're going to take the degree of each and multiply by pi over 180. So when we do 10 degrees, we're going to get 10 times pi over 180. That's what we're going to get. And when we do that, it's going to be 10 pi over 180. And when you simplify that, that's going to be 1 pi over 18. Just like that. Right? Now, we got all that together. You're going to do the 20, 40, and the rest. So pause this video and do this right quick. Pause the video and try to do it yourself. Alright. Welcome back. Before I show you my answers, let's just do 20 degrees together. So 20 times pi over 180. So that's going to be 20 pi over 180. And when we simplify that, because we can get rid of the zeros. That's going to be 2 over 18. And 2 over 18. And then remember this is pi. You could leave it as 2 pi over 18. Or if I actually simplify this out of the way, it's going to be pi over 9. And that's how you do 20 degrees. So if you miss any of that, just pause here and rewind. Alright. So now I'm going to show you my answers. And we're going to leave it as that. So here we are. Do it exactly as I did. There's no surprises here. It's just doing the same steps over and over again. Alright. Now it's time for us to do our math rotations. You're going to meet with me. So in M, we're going to prove the Pythagorean theorem. But now we should already know what the Pythagorean. Alright, so let's go ahead and prove the Pythagorean theorem by using the notch of that circle. So let x and y represent any point on the circle with a center at the origin and with the radius of 1. And we're going to use using the circle equation, you get this guy right here. Now, this circle definition is what's going to give us our new type of Pythagorean theorem that we have never seen before. So let's do it. So we know that H and K being center points is at the origin, so it's going to be 0, 0. So let's plug those in. We get that. And with the radius being 1, so that's just going to equals 1. After you get through with that, you're going to be left with x squared plus y equals 1. X squared plus y squared equals 1. And then when you square root both sides, you get x plus y equals 1. So it's just like the Pythagorean theorem. It is the Pythagorean theorem. The Pythagorean theorem was built off the circle definition. I know in middle school you probably saw it a bunch of rectangles that looks like this, whatever, what have you. Oh, I cannot draw. I need to stop. But you get the point that I'm trying to make here. You've seen this, but you've seen this look using grids and stuff. However, when you get to high school, which you guys are at, and right now, you will use the circle to derive the Pythagorean theorem. The circle is the Pythagorean theorem. The circle is the Pythagorean theorem. R is your what? So matter of fact, let's label these pieces since we prove it. So your X is your adjacent, right? Your Y is your opposite leg. And then R is your hypotenuse. In our next lesson, we're going to, we're going to derive trig ratios and all of that. And again, you just use the knowledge of the circle. All together, you're going to fill the unit circle degrees and you're going to convert degrees to radians and vice versa. So when you try to build a unit circle, these are the most critical, critical angles that you're going to be dealing with: 30, 45, 60, and that's one more that you're going to be dealing with: 90. These are the four most critical angles because they're going to set the tone of what you do to create all of that unit circle. So these are the four that you're going to use. In that class period, you're going to see how they work to build them together. But at this moment, I need for you to build a unit circle by degrees and converting the radians. So go ahead and create this with the unit circle using your 30, 45, 60, 90 knowledge. I want you to create this unit circle. T, technology. So we're going to probably fill in the unit circle and the degrees and convert. Hands on. It's going to be that same thing. Alright, yeah. Oof, I'm sorry. That's it.